Hello. So in this lecture, we're going to introduce the idea behind deep learning and neural networks. So the reason we're doing this now is because if you've been following the reinforcement learning series, we reached a point whereby we would want to utilize neural networks in order to build more powerful reinforcement learning algorithms. But if you've not been following that series and you're just interested in learning how neural networks work, you are interested in learning more about deep learning, then this upcoming series of lectures might be helpful for you in that regard. Having said that, let's get started. So the first thing we need to talk about is what kind of problems can we solve with neural networks? So immediately we can look at what are known as regression problems, and we can look at something known as classification problems, right? So regression problems are just problems whereby we are predicting a continuous variable, right? So we are predicting a continuous variable. So things such as price, sales, this type of stuff. So let me actually give you an example of this. So let's say you are trying to, you are a business, you have a lot of stores in different locations, and you're trying to open up a new store in a new location, and you're trying to see how much sales you're going to make in the first year after you open. So what are the important features here in predicting the sales, right? So the first thing you can think of, so let's say, let me actually write this down. So the first thing you might think of is like, okay, the location itself is important, right? That's one feature that's important. Another important feature might be, okay, the number of competitors in that location, right? Because that will also affect like how much sales you can make. And another feature you can think of is maybe like how accessible the place that you're trying to open is. There are all these different kind of features that we can think of. And so I'm just going to show them by this like continuous thing. But the idea here is that each of these features has an important weight when given the task of predicting sales. So these things that we're looking at, location here, let's just call this, let's call this X1, right? And we look at number of competitors, let's call this X2, right? Plus other probable features are important when we're trying to predict Y, which is what? Our sales, right? So this is what we want. This is what we want to predict, right? And these are the features we have. And how do we weigh like what features are important when we're trying to make this prediction? Well, we multiply each feature by a set of weight. So we say W1 times whatever the value of this feature is, right? And then plus W2 times whatever the value of this feature is, and so on. So yeah, I'm just giving you a rough idea of like what features are and what like the target we're trying to predict actually is. So typically that's how we solve for regression problems. So I actually have another like lecture in the Bayesian machine learning series that actually talks more about how we solve for regression problems in particular. So if you're interested in learning more about this, then I'll link the video in the description, but you can take a look at that as well. Since we won't be focusing so much on this, at least in this introductory video, but we'll be looking a bit more into classification. So classification is essentially predicting a categorical variable, right? So an example of this is, for instance, you're given, let's say, a picture of a dog or a picture of a cat, and you want to predict whether it's a dog or a cat, you see. So they're like, it's either one or the other. That will be what's called a binary classification problem. But of course, you can have multiple classes and so on. So another example, which we'll actually be working with when we actually build our own neural network in the next lecture, is analyzing, for instance, digitized images of, let's say, cancerous cells, and you're trying to determine whether those cells are whether those cancerous cells are malignant or benign. So let me actually write that down to make that clearer. Right, so this was our typical regression problem, right? So let's say instead we're trying to solve for a classification problem. So we're analyzing the characteristics, right? So we are analyzing the characteristics of cancer cells, right? And we're trying to see whether they are malignant, which means they're very infectious, or they're benign, right? Which means that they are not harmful. So what are the important features? What are the things that we look at? What are the things that medical practitioners look at when they are trying to determine whether such cells are malignant or benign? So the first thing is, well, you can look at something such as we can look at the radius, we can look at things like the texture. So you'll understand this more when we work with the data set in the next lecture. But I just want to bring about a larger concept here. Maybe we can look at the perimeter and so on, right? So again, this is our x1, which means it's our feature, x2, another feature, x3, another feature, and finally, the thing we're trying to predict, our y, right, is two classes. So either this is going to be malignant or benign, right? So if it's malignant, then let's say the class is +1, and if it's benign, it can be maybe -1, right? Or it can be +1, -1, it can be 1 or 0, it doesn't matter. That's not the point here. But the important point is we are given these features that are important in making us like classify whether this cell is malignant or benign. But we need to estimate how important each feature is, right? So we have W1 here, we have plus W2 here, plus W3 here, right? So you'll see there's a pattern here. First, in the regression problem we're trying to solve here, and in the classification problem we're trying to solve there. So this is our classification problem, right? And we see a pattern whereby we're essentially taking each feature, we're multiplying it by some weight, which tells us how important that feature is in making this classification, right? You can think of it that in a loose way, but this is essentially the pattern we're seeing here. So in general, what we can say is for us to make our prediction, right, we can define Z to be equal to W1 x1 plus W2 x2 plus W3 x3 all the way up to Wn xn, right? And so x here is our feature, and W here is just the weight that we're attributing to that feature, right? So now, since we're solving for a classification problem in this case, so now we're done with looking at this regression, right? And we'll go further down later on in later lectures, rather. We will analyze this in more detail. But right now, I just want you to understand the concept that for each feature, we multiply it by some weight. And then what we do is we compute what we call phi z, right? And we say this is equal to 1 if z here is greater than some threshold, theta, we just call theta, or -1 otherwise, right? So this is essentially our prediction, right? So first of all, we compute z where we're multiplying these weights to our features. And then we say that phi of z is equals to 1 if z is greater than theta or minus 1 otherwise. So the one thing you notice here already is that, okay, this is essentially our prediction, right? So let me write. This is essentially our prediction. So it's either going to be correct or incorrect, right? And whether it's actually going to be correct or incorrect highly depends on the values of W, right? How do we actually come up with these weight values, right? So we're going to briefly discuss that shortly. But first of all, I want to rewrite this expression here, whereby we say, okay, we say phi z is equals to 1 if z is greater than theta, some threshold, again, another parameter that we define by ourselves, right? Or minus 1 otherwise. So the way that we can rewrite this is, well, if we look at z is greater than theta, we can also write it as z minus theta is greater than 0, right? Yeah. This is just a direct, we can infer this from this. So that means instead of writing it in this manner, what we can do is we can say, okay, if we say that, let's say, let me just write it like that, our z, right? If we put the minus theta that side, we can just write it instead as minus theta plus w1 x1 plus w2 x2 all the way up to wn xn, right? And what we can say here is if w0 is equals to minus theta, right? And x0 is equals to 1, then we can actually rewrite this, right? Z is equals to w0 x0 plus w1 x1 plus w2 x2 and so on, wn xn, which is equals to w transpose x, right? So we can now write this in this vector. We can compute this dot product of this feature vector and this weight. And we will realize the importance of this later on. It's actually quite efficient to do things this way rather than like computing these multiplications in this fashion. But we'll dive into that later. And then we can rewrite this as now phi z, right, is equals to 1 if z is greater than 0 minus 1 otherwise, right? And essentially, we call this W0, whatever, we call this our bias term. So I'm not going to talk about the why we include this here. Actually, if you're interested also, when I was looking at the regression problem here in the other lecture that I'm going to link in the description, you'll see like why we need this term to begin with. But for the purposes of this lecture, I'm just going to skip through that so that we can cover more ground here. But if you're interested in learning more, I'll talk about it later on, or you can also watch that other video. So that should also be fine. So this is it. We have established this way of thinking whereby we say that, okay, our prediction is equals to 1 if z is greater than 0, and it's equals to minus 1 otherwise, right? And this actually brings us to the simplest version of a neural network we can think of, which is known as a perceptron, right? So we're gonna talk about what is called a perceptron. And the way we can think about it is as follows, right? So essentially, we're given our features, so say x1, right, x2, and x3. And once again, Our features is whatever variables is important, like whatever variables are important in helping us make some prediction. So it could be helping us in making prediction on sales, on price, on whether a tumor is malignant or benign, and so on. So these are our features, right? And we feed them to this perceptron neuron, right? And then we get our output, which is our prediction, right? But as you can see, what we do is we feed them here, we multiply them by a set of weights W1, W2, and W3, right? So we multiply by the set of weights here. Then here we apply our step function, right? We apply the step function and we get the output. And by step function, it's actually this thing here that we showed here. Because if we actually plot it, if you actually think about it, let me plot it here, right? What we actually have is something like this. Like if this is, let's say, W transpose X, right? And then this is phi of W transpose X, which is essentially our, again, prediction. What we're saying is, let me use a different color here. We're saying if it is greater than 1, if W transpose X here is greater than 1, then, it's greater than 0, then the class is 1. If it's less than 0, then the class is minus 1. So this is called a step function, right? It's just a way of us to threshold our predictions, right? To say, okay, we compute this W transpose X, our weight vector times our features, and either it's going to be a positive class or it's going to be a negative class. That's essentially the meaning behind this. But one thing you might ask yourself at this point is, well, again, we still don't know how to compute W, which is also true in this case. And we're actually going to learn how we can do that. But here I introduced a step function. I just want to introduce something else. So actually, let me create a new page. Right. So let me introduce what is known as a sigmoid function. You'll understand its importance in a minute. So what this does is it sort of acts like the step function, except, let's say, it looks like this, and it comes down here. Okay, I think I can draw this better. Yeah, that's a little bit better. So this is essentially equal to 1 here, and it's equal to 0 over here, and at this point it's 0.5, right? So this is what our sigmoid function looks like, right? So we could essentially, instead of having this step function here as being our phi of z, because phi of z is using a step function, it is hard, like you can see that if z is greater than 0, it's 1, otherwise it's minus 1. We could instead use a sigmoid function, and this goes all the way from infinity to minus infinity. Right, we could use this instead, and what it does is, given our W transpose X, right, our prediction, what it outputs is, like, if W transpose X is greater than 0, right, it's going to give us a value that is greater than 0.5. If W transpose X is less than 0, then it's going to give us a value less than 0.5, right? That's how it works. So with this sigmoid function, we can actually get a probability, right? So we can think of it as saying, what is the probability that this function is no, that this cell is, or this tumor is malignant, or is it benign. So it can actually give us actual probabilities, and this can also work in some way as some sort of like confidence in our predictions, right? And if you wanna hard like code it and say that, okay, if the probability is greater than 0.5, then it's 1. If it's less, then it's -1. But the main attractive nature of this function as well is that it is, at least in this case, differentiable. So one thing I should mention before actually going into how we are learning these values like W1, W2, W3 is that a perceptron only works when we're dealing with, let's say, problems that are linearly separable. So I'll give you an example, right? So separable, right? So what happens is this: if we have, we're trying to make our prediction, right? And then we have, let's say, a few samples here. These are the positive class, right? And then we have a few other samples where this is our negative class, right? And we're trying to make our prediction. Usually what we're doing is we're creating a decision boundary like this, right? Where we say that, okay, anything that falls to the right of this decision boundary is classified as a negative class. Anything that falls to the left of this decision boundary is classified as a positive class. It's sort of working like how what we had over here, right? But if we have data set that is not linearly separable, right? So an example of this would be something like, okay, let me write this here. Okay, let me just follow through. Okay. Sorry about that. So non-linearly separable data. So we would have something like this, let's say. So let's say we have our positive class like that, and let's say our negative class is like this, right? And you can think the decision boundary in this case would be something like that, right? So this is linearly separable data, and this is non-linearly separable data, right? So a perceptron can handle cases like this, but it cannot handle these cases. So that's something to keep in mind as well when we are defining these perceptrons and stuff. Okay. So having said that, let's actually get to our next point, which is what we're actually trying to do here is fine. We're given a set of features. We are trying to multiply them by some weights that we're going to learn to get our predictions, right? So what we've learned so far is that we're given some features, right? X, right? And then we multiply them by W, some weights, right? And then we feed them through some thresholding function, right? Then we feed them through some thresholding function called, let's say, phi of z or whatever. And after doing that, we get our prediction, right? Let me actually write it. We get our prediction. So these are the steps we've been taking. Get our features, multiply with some W, then put them through some thresholding function, and we get our prediction. But the issue now is we don't know how to actually compute this W. In the beginning, we might just assign random values for W, but of course, if we assign random values, what's going to happen is our predictions are not going to be accurate, right? We're going to make mistakes. So let's actually walk through some example, right? So let's say we have a data set, right, where we have our features. Let's define a data set here. So we have our features. Let's say we've got entry 1, we have feature x1, x2, right, x3 or whatever, and they take whatever values that they take, and then let's say the target variable, it could be sales, it could be price, whatever, let's say y. We call this y the target variable, right? The target. The target variable is what we want to predict, right? Okay, this is our y. And then we call this y bar. This we call our prediction. Okay, so we have cases like this, right? We have our table here. We have our target variable, we have our prediction. Prediction has been made from these features, right? x1, x2, x3, whatever they might be. You don't need to concern yourself with those now, right now. So for the first entry, let's say the target variable say the value is 200, but our prediction is something like, oh no, it's 100. And for the second one, let's say it says it's 50, but our prediction says it's 0. For the third one, let's say this says it's 10 and the prediction says it's 10. And for the fourth one, right, and so on, right? So as you can see, for every prediction we're making, right, there is going to be some error involved. So actually, to make this clear, let me just make this 20 here. Okay. So for instance, there's an error involved here. So for instance, here the target variable is saying it's 200, but the prediction is 100. So the error here is 100, right? Well, depending on how you define your error. And here it's 20, and here it's 0, or whatever. So we add up all these errors, right? And let's say the sum up to something like 500, right? This is the sum of errors, the sum of our errors. But now the problem is these errors, this is what we are trying to minimize. We want the predictions to be as close as possible to our target variable. So we're trying to minimize this error. So if they start as 500 due to our random set of weights, because again, if you remember, we're getting our prediction, y bar, right, by taking the phi, some threshold of, say, W1. Actually, let me just remove this phi and just show the simpler version. Let's say W1, X1 plus W2, X2, and so on, right? Or in this case, plus W3, X3. Let me just end it here, right? So we're taking our features and we're multiplying them by some weights, and that's what's giving us the prediction here, right? So, of course, here we can apply like a phi function, like a sigmoid function, which is called an activation function. But I don't want to talk about this right now. I just want to show the simpler case where we're solving some, say, simple regression task. So this is our prediction, right? So as you can tell, this is for a regression problem where we're predicting something continuous instead of a classification problem. But I'm just doing this because it's much simpler in this case. So given this, so we predicted 500, right? This is y bar. So what can we change here in order to make the predictions closer to the actual? We want to minimize this error, right? So the only thing we can change is w, right? We can change the value of w so that when we do this multiplication, maybe the next time, it will be closer to 200 here and closer to 20. So here the error is quite high. Here it's small, and here it's right. It's okay, right? So we want to modify w so that we minimize this total errors, right? So we define what is known as a loss function, right? Because a loss function enables us to take our to actually measure like how costly our current set of weights is, and then think about how we can actually minimize this. So there are different types of loss functions we can define depending on the problem we're trying to solve. So I'm not going to go into like too many details on loss functions right now. I'll leave that for a separate lecture. But the idea here is that given a loss function, what we are trying to do, we define a loss function, L, as a function of W, right? And what do we actually attribute it to? It's going to be a function of y, right? Whatever our it's going to be something related to y and whatever our prediction is. So actually, let me give an example loss function instead of writing it more generally. So it could be something like take y minus y bar squared, right? So this is an example loss function, right? This is an example loss function, y minus y bar squared, right? So what is this one saying? It's saying take the prediction and take the prediction and the target and subtract them and then square them. So what this loss function does is it actually penalizes items that are far from each other more. So if here we have a loss of 100, we are going to take 100 squared. Here we're going to take 20 squared, and here we're going to just take 0 squared, right? So there are many different kinds of loss functions we can define depending on the kind of problem we're solving. Here I'm just showing you an example of a loss function, and each and every loss function has different motivations based on why you'd want to use it. But the idea that I'm trying to show here is, let's say for instance, we define our loss function, right, L of W, and let's say it looks like this, right? This is what our loss function looks like, right? If it's squared, for instance, we can tell this. So let's say for the current W, right? For the current W, the loss is, we say it's like, let's say it's 500, right? And this is for our W, right? So our current set of W has this cost, right? So what we are trying to do is we are trying to minimize the cost. Right now the cost is 500. We're trying to find values of W that actually minimize the cost. So if you remember from calculus, if let's say you're given a function like this and you're trying to find the minimum point of this function, what you would do is you would take the derivative of the function and equate it to 0. Because by taking the derivative and equating to 0, you find the minimum point. And as you can imagine, in this function that I showed you here, the minimum point is right here. This is where the loss is minimized. So whatever the value of W is at this point, so value of W at this point is what we want, right? So it does, of course, like this function can like take many forms, but here I'm just showing it like a simple version of it. So the idea is that, okay, we are given the current value of W and we take the derivative. If we equate it to 0, then we can get to the minimum point. But the problem lies when we've got multiple variables involved here, right? Because usually when we're looking at this, we're just dealing with maybe one variable. But if we are dealing with multiple variables and we've got more complicated like prediction functions here, then what we would need to do is use a method called gradient descent, right, in order to actually reach this minimum point. So because if we try to just equate the gradient to 0, then we're going to be solving a system of equations that might actually end up being more complicated. So you don't need to focus on these points right now. They'll come clearer as we go on to the next lecture and so on. But the thing that you need to capture here is that, okay, let me actually show it here. So given, let's say our W here, we are trying to minimize it, right? We're trying to minimize this loss function, right? So the way we minimize this loss function is by taking the derivative, right? And then we move in a direction opposite to the gradient. What does that mean? It means at this point, right, we have our W. So what we're going to do is we're going to compute the gradient here, right? We're going to compute the gradient, and we can see that the gradient is positive here. And then what we do is we take a step, we update W by taking a step opposite to the gradient, right? So we take a step opposite to the gradient. And that's why this method is called gradient descent, because what it means is we update W by saying W, right, is equal to W minus the gradient of, like, with respect to W of the loss function, right? So as you can imagine, like if we are just, usually when we're taking the gradient, of course the value is going to be like, oh, I mean, it actually depends, like sometimes it can be high, it can be small, but the point is that we need to multiply this by a parameter called alpha that we call the learning rate. And the reason we do this is it's going to determine how big a step we're going to take, right? So this determines how big a step we take. So we multiply our alpha, we multiply our gradient by the learning rate. So if alpha is too big, right? Actually, if alpha is too small, then what happens is we end up taking very small steps, and it will take forever before we actually reach the minimum point. But if alpha is too large, then what ends up happening is, like, maybe we're at this point and we take our next step, and then we're going to miss the minimum point and we're going to end up here because we chose an alpha value that is too large. So we need to make sure that we take the right value of alpha. So if we're already seeing a few complications here with this, so if there's anything to take out of this, is number one, right? We need to choose the right loss function for the problem. So we need to choose the right loss function for the problem we're trying to solve, right? And the next thing we need to think about is choose the right learning rate in order to make sure that, first of all, if it's too small, we will learn very slowly. If it's too fast, if it's too large, then we might end up diverging, right? So there's always a middle point whereby we try to choose the learning rate, the right learning rate, and we try to choose the right loss function. So in the future lectures, we are going to look at how we can actually go about choosing the right loss function and the right learning rate for a problem. But Yeah, so for this lecture, I just wanted to introduce the general ideas behind. Well, first of all, we've covered the differences between regression and classification problems. We've covered what a perceptron is and how we can make our predictions using a step function. How instead we can make use of something known as the sigmoid function, which gives us a probability of something belonging to a certain class. And then we saw that the problem with perceptrons is that they only help us in solving like linearly separable problems. When a problem becomes nonlinearly separable, then it becomes a bit hard to use perceptrons, unless of course we start dabbling in a bit of like using like more complicated features as well, which is something I also cover in the statistical machine learning lecture if you're interested. And then we looked at an example data set, which was, of course, for a more like a regression problem. And we defined what a loss function is and why we need to use a loss function. And that is, it will tell us the cost, essentially, of our weights, right? And the cost itself, if it's too high, what we want to do is we want to change the value of W so that the cost is low. Because as the cost being low means that the sum of errors here is going to be low, right? It means that the target and the prediction are going to be close to each other. It means that we're doing something right, right? And the way that we minimize this, of course, in a simple case, right, we can take the derivative, equate it to zero, and we have a function. But in cases that we deal with, like in realistically, we need to make use of a method called gradient descent, where we take small steps trying to reach the, it can be a global minimum, it can be a local minimum, it depends on the kind of function we're dealing with, right? And we looked at how we actually update the weights, and we update them by making use of this function where we say W is equals to W minus a learning rate parameter, which determines how big a step we take and the gradient itself. So finally, we said we need to choose the right loss function for the problem, and we need to choose the right learning rate for the problem. And this lecture will just introduces the idea behind like how we can create something like a perceptron. But in the next lecture, we will continue from this point and start talking about building neural networks, and we look at the backpropagation algorithm. So yeah, I think I will end it here for now, and I'll see you in the next lecture.